So let us solve sample problem involving electric potential due to a collection of point charges. So the problem goes this way. An electric dipole consists of point charges Q1, which is 6 microcoulomb, and Q2 equals negative 6 microcoulomb, placed 16 centimeter apart. So we'll compute the electric potentials at point A, point B, and point C. So we will base the problem on this figure. So point A is 9 centimeter from Q1 and 7 centimeter from Q2, while point B is 7 centimeter from Q1, and that's 7 plus 9 plus 7, that's 23 centimeter from Q2. Point B is 23 centimeter from Q2, while point C 16 centimeter from Q1 and 16 centimeter from Q2. Q1 here is positively charged, and then Q2 is negatively charged particle. Okay, so let us compute first the potential at point A. So the potential can be determined by the electric potential energy over the test charge Q of O, and this one is equal to the Coulomb's constant over times the summation of all ratios of charge over distance. So the point charge, the electric potential at point A is equal to the Coulomb's constant times Q1 over R1. R1 is how far point A from Q1, plus Q2 over R2. R2 is how far the distance of point A from Q2. Right. So Coulomb's constant is 9 times 10 to the power of negative to the power of 9 Newton meter squared per coulomb squared, times Q1 is, that's 6 positive 6 microcoulomb, and that's equal to 6 times 10 to negative 6 coulomb, over how far is point A from Q1. That is 9 centimeter, so that's 0.09 meters, plus Q2 is negative 6 times 10 to negative 6 coulomb, over R2, how far is A from Q2. That's as you can see in the figure, point A is 7 centimeter from Q2, so that's 0.7 meters. So we'll compute using protractor. We'll compute using calculator. So the potential at A is equal to negative 171,428.57 joule per coulomb, and 1 joule per coulomb is 1 volt. So the potential, the electric potential at point A is negative 171,428.57 volts. So this is the electric potential at point A. So next, we will compute the electric potential at point B. So again, the electric potential is the ratio of electric potential energy over test charge Q of O, which is also equal to the Coulomb's constant times the summation of all ratios of charge over distance R. So we have the potential, the electric potential at point B is equal to the Coulomb's constant times the charge Q1 over R1. R1 is the distance of B from charge 1, plus charge 2 over R2. R2 is the distance of point B from charge 2. Alright, so what's Coulomb's constant? That is 9 times 10 to the power of 9 Newton meter squared per coulomb squared. Multiply by, what's the charge of Q1? Charge of Q1 is 6 microcoulomb, so that's 6 times 10 to negative 6 coulomb, over how far is B. As you can see in the figure, point B is 7 centimeter from Q1, so that 7 centimeter in meter is 0.07 meters, right? Plus Okay. The charge of Q2 is, what's the charge of Q2? Negative 6 microcoulomb. So this is negative 6 times 10 to negative 6 coulomb over how far is point B to charge Q2. So this is 7 cm plus 9 cm. That's 6, yeah, plus 7, that's 23 cm. So in meters, that is 0.23 meters. Okay, so again, let us compute using calculator. So the potential at point B is 536,645.96 joule per coulomb, and 1 joule per coulomb is 1 volt. So the potential at B is 536,645.96 volts. So this is the electric potential at point B. So next is to compute the electric potential at point C. Right? Point C is 16 cm from Q1 and also 16 cm from Q2. Alright, so the potential at C, electric potential, is Coulomb's constant times Q1, the charge of particle 1, over how far is point C to Q1, plus charge 2 over how far is point C to charge 2. So Coulomb's constant is 9 times 10 to the power of 9 Newton meter squared per Coulomb squared, multiplied by charge of Q1. Charge of Q1 again is 6 times 10 to negative 6 coulomb over R1, how far, that's 0.16 meters, plus R2 plus Q2 is negative 6 times 10 to negative 6 coulomb over 0.16 meters. Okay, so if you're going to add these two, then you have the sum of 0 multiplied by the Coulomb's constant. Then the potential at C is 0 joule per coulomb, or the potential at C is 0 volt. 0 volt.